All right, third time's the charm. Welcome back to another video on Duck Game Computing. Now featuring a nice snake shed on my wall next to my V12VR poster. Uh, Today we're talking about feed tapes. So what do we mean by that? Feed tape is a way to physically store data. Uh, Ideally with a way to read and write it. So for this we're using blocks in Duck Game. Writing blocks in Duck Game is very simple. We can connect spawn cannons to buttons and other wires and other logic to write that. Reading is the tricky part. So, very important feature is the present to make all this work. So the present has, first of all, has collision, so you can stack other boxes on top of it, to make sure that all the items in the feed tape keep their order. And you can also, presents are also the only block, as far as I know, that has that trait and is also completely just ignores bullets. So you can shoot right through them. They don't block bullets. They don't get destroyed by it. They don't interact with them at all. And so what this means is that we can set up if we want to read a feed tape like this, we can set up a contraption to manually try and shoot through every single block in the feed tape, with a line with some destructible objects on the other end of the feed tape. And if we can't destroy anything, then we know it's not a present. If we can't destroy something, we know it is a present. So that's two different states we can read. We have 1 and 0. We're in business. We have a feed tape. So why this might be practical, I'm gonna be real. I made this because I had the idea and I thought it would look cool. Why it might be useful in Duck Game to store data in a physical sense, I don't think requires too much explanation. I can store a byte or a bit of data in a single block, or I can store it in one of my giant registers from previous videos. Obviously, the different ways of storing the data may prove easier or harder to work with, but it's an alternative and it looks cool, so that's why I'm showing it off today. Now, presents have a very annoying feature about them. They are slightly shorter than a lot of other blocks, and because of that, they are prone to stacking up. I have a sequence here of 8 blocks, some presents, some TVs. And if you can imagine how I'd be moving these things around in a real Duck Game map where I'm trying to manipulate feed tapes, I'd probably be moving them with like teleporters, pipes, ice wedges, trampolines, water flow blocks, all sorts of things. And presents tend to have a nasty habit of stacking up or causing objects behind them in the chain to stack up. And so what do I mean by that? Well, I have 8 blocks up there. They're going to fall into this water flow entity. And then if I count the stack over here, it's only 6 blocks tall. What's happened here? Well, let's dig through this. So that's a present. We remove this. There are 2 presents stacked in the same spot. These are all singles. And then we'll see behind this here, there's 2 TVs stacked in the same spot. So if you are moving things around a lot, you might have some problems with that. And so I have some simple devices here to demonstrate. So this one up here is just a way to randomly generate a byte. It's just a hold button here that keeps this gate open for half a second. Which half a second is long enough for this clock here, this block falling between the 2 teleporters, to hit this button exactly 8 times and randomly generate 8 blocks. And then this contraption over here just counts out 8 blocks before opening this door to make sure all the items are nice and neatly together, and then drops them onto this water flow entity. Because the blocks are so tightly packed and also moving pretty slow, it means that the water flow entity won't cause the items to stack up like previously. So if I generate it again, you look at the water flow, 1, 2, 3, 4, 5, 6, 7, 8 blocks. Very nice and tidy. This isn't necessary for all contraptions. I just figure this is a handy thing to know how to do to separate out the blocks in a feed tape, to avoid stack ups. So I'd figure I'd share that. Anyway, now that we know what it is, let's move on to the fun part, which is reading these feed tapes automatically. I am very proud of this contraption. Here we go. Here it is. Not that crazy big, but there's a lot going on. So the way this works is a feed tape falls in here, a stack of 8 blocks. We got one lined up right up here. And then it hits this button. This button starts the whole system. It opens this gate, which causes this present to fall through. This makes this clock start going. So every time the present goes through this loop, it hits this button once. That button shoots the mag blaster to try and destroy a crate on the other end of the feed tape, as well as opens this gate for just long enough to allow a single block to pass through. And then over here we have a selector. So it's not showing visually right now, but the output from this button and the inverse get fed into a single NAND gate each. And then when we want this signal from this button to propagate through to the either TV or present spawners, we can enable that with the clock signal over here. So this is going down here and then through this spawn cannon through the teleporters up over here. We need to sync this up. If we want to make this go fast, we need to sync these things up very precisely. So that's why I'm not using a wire down here. We're using a spawn cannon and teleporters to ensure that the race that we have roughly an even race between this mag blaster signal propagating to this end of the NAND gates and the wire signal propagating to this end of the NAND gates. And then we have our spawn cannons to print out the copies. So let me show you this all in action here. Oh, one other detail. This is the first time I've had a reason to use these in a circuit. With the way this clock is set up, there's a lot of tiny reasons I had to set it up like this. You can almost certainly reorder it to maybe remove these metal doors, but they look cool, so I'm keeping them there for now, and I haven't been bothered yet. These metal doors just ensure that once the feed tape gets read out, that these doors will close and ensure that no more bullets can get shot through and potentially send fake signals into our selector here, either from the mag blaster or from this spawn cannon over here. So anyway, let's show it in motion. It's so fast, dude. I'm so proud of this thing. So as you can see here, this is the original, 8 blocks tall. This is the copy, also 8 blocks tall. Every single TV has printed out a new TV. Every single present has printed out a new present. And just to demonstrate here, we can send in some different combinations. Here's a lot of TVs, one after the other. Perfect copy. Here we have even more TVs. Let's see if we can get one with a decent number of presents in sequence. Yeah, there we go. As you can see, perfect copy, nothing stacks up, 8 blocks, beautifully separated out. In this map, you'll also find a copy, a mirrored version of it. For whatever reason, I have both manually built a copy and then also tried using the flip function in Duck Game. If you select something, you hit F, it'll flip it around. It's not perfect. You're going to have to manually change some stuff around. But it can have its uses. I've tried both those methods to create a flipped version, and there's always slight timing differences. For whatever reason, the logic with the selectors doesn't quite match up. And so if you're working with these yourselves and you're finding hiccups and the readers aren't working as you intend them to, I just want to show you a few knobs you can mess with. The main difference you can see between these two is, one, I've extended the clock out slightly. It is 1 block taller, so it clocks at a slightly slower rate. And then also I have added 2 extra wires of delay for the connection between this button and this input of the NAND gate. As you can see down here, it's just a straight line, and here we drop it down 1 and then run it over and then go back up. So you can mess with the clock length, you can mess with this signal length, and then also you can adjust this spawn cannon angle. Currently it's angled 5 degrees up to ensure that just barely enough time passes between this mag blaster shooting this crate and the next crate spawning to leave a wide enough window for the selector to work properly. Otherwise, you might get like both a present and a TV printed for reading 1 block, which wouldn't be ideal. So those 3 things, this wire, this spawn cannon, and the clock, are the easy knobs to turn to try and get all your timings to line up properly in case you're trying to use these things in your own designs. Anyway, that's the reader. That's the basic concepts. Now I want to talk about a little bit of an overlap between Duck Game and what I actually do at work. So I am a computer engineer. I do verification on digital circuits. If you design a digital circuit, you can simulate it, emulate it, and do all the testing there. And then once you have a design you like, you ship it off to a fab to get printed. Or to get produced, and that is a very expensive process. You'll create either little just microchips or integrated circuits, what have you. But you order in bulk, by the millions, and it costs millions of dollars to print. So when you send that design off, you have to be damn sure that there's nothing wrong with it. There's So you could try and manually test everything with unit tests, every single edge case, every single weird situation where you want to make sure that it works right. You could try and test all that, but inevitably something is going to get missed. It's just not a reliable way to test things. So the industry standard is called a universal verification method, where you just spam a whole lot of inputs into a design, and then read the outputs and make sure everything lines up accordingly. And so by sheer brute force of random inputs, you are eventually going to cover everything, to cover every possible combination and sequence and bit and all of that. And so I have set up a very simplified, incomplete UVM test bench for the copier that I've made. So the way this works is we have our random sequence, our random inputs are going to get spammed out of this byte generator up here, fall into the copier. Copy is going to get made, and then each copy is going to fall into its own reader. These readers are going to read through, and then we've connected up the outputs of these crate buttons to this XOR gate over here to make sure that both of them are always turning off or on at the same time, which would mean that all the blocks getting read through the reader are the same blocks. And then down here we have a length comparison. So that's just hooked up to this button, the enable for the entire reader. So this just ensures that both these buttons are on and off at the same time. And the reason they wouldn't be is if one byte on the left, for example, is 7 bits long, and then the byte on the right, or the feed tape on the right, is 8 bits long. Then this would spit out a yellow barrel for a length mismatch, and then if there's just a block difference between them, like one side's a present, one side's a TV, we get a explosive barrel as a block mismatch. And so, I mean, really the fun part is just watching this all in motion. Look at this. It's beautiful. I am very proud of this thing. So right now, we can leave this running for a while, and no errors most likely are going to show up, bar some weird duck-in physics stuff that I haven't quite sorted out. There's a pretty big asterisk on bigger contraptions, but we'll cross that bridge when we get there. But let's manually insert a bug here. So here we've shortened this by 1. We should get 2 block mismatches, maybe 3, and also a length mismatch. There we go. So 3 block mismatches and a length mismatch. We can also go to the other side and add another little length mismatch here just to demonstrate. It works on both sides here. There we go. And we get another length mismatch and a whole lot of block mismatches. So we could leave this running for a while from a clean slate. And then after a given amount of time, we say, okay, it's probably covered everything. And then we can read our error outputs to see if anything went wrong. Another nice thing on display here, which will become much more relevant in future videos, is pipelining. While I could have the sequence loop once it's done, so we could set up the system that it makes a copy and then reads both copies, and only when it's done reading both copies does it loop back and restart the system. Or because the copying and the reading parts don't really overlap, we can separate those two things out and each be their own stage of a pipeline, so we can have them both operating at the same time. So as you can see in this system, we are generating new bytes and copying those at the same time as we are reading things. I'll get much more into detail about this in future videos, but it's a way to speed things up, as you can see here. Yeah, I think that's about all I've got for today. Just let you enjoy this view for a little bit longer. Map downloads for everything are in the description. Next time, I'm going to talk about shift registers. So this wasn't the last video. We got more content. Yeah, so that's about it. Thanks for watching. See you guys later. Bye-bye.